Good afternoon, everybody. I hope everybody's doing good. We're looking today at lesson 31.04, which is the final lesson in the current handout. I'm going to be reviewing some basic ideas behind rational functions, but our focus here in this lesson is on asymptotes. You already know how to find vertical asymptotes, which we're going to review in the first part of the lesson with our rational functions review. But we're going to be analyzing the vertical asymptotes a little bit differently than you would have in Math 30-1. And we're also going to be looking at finding horizontal asymptotes, and we're going to be finding these in a totally different way as well than you did in 30-1. Those of you that are in this course and are still in Math 30-1, don't fret over some of the stuff we're going to be talking about. When it comes time to use it and you need the information taught to you in detail, we will worry about that then. All right, let's get started here. And a quick review of what a rational function is a rational function is a fractional function, if you like, but what makes it rational is that the numerator and denominator are functions of x. And because the denominator is a function of x, there's the potential for the denominator to be equal to 0. Very, very simple rational function might have a denominator of x minus 3. Well, if x minus 3 is the denominator, then when x is 3, the denominator would be equal to 0, and that's not allowed. You're never allowed to divide by 0. So because the denominator is a function of x, that introduces the idea of having what we call non-permissible values of x that you're not allowed to use. Now, the non-permissible values that you get by looking at the denominator of a rational function could exhibit themselves on a graph in one of two ways. They could reveal themselves with the appearance of a vertical asymptote, or what might be there instead of a vertical asymptote is a hole in the graph, sometimes called a point of discontinuity. Now, I can sense that those of you in Math 30-1 right now who haven't learned any of this might be getting a little antsy at all of this, but I want to make one point very, very clear here. We don't care about holes in graphs today. We're only looking at asymptotes. What you need to remember or know is that if that factor in the denominator cancels with an identical factor in the numerator, then it's a hole. And we don't care about that. All we care about knowing is that if it cancels, we're not going to worry about it because it's a hole, it's not an asymptote. On the other hand, if the factor that produces the non-permissible value does not cancel, then it's a vertical asymptote. So we don't care about the holes, we do care about the vertical asymptotes. We're learning about when we get a hole and when we get an asymptote so we know what we need to concern ourselves with. All right, let's take a look at a warm-up which has nothing at all to do with holes or points of discontinuity. You're given a graph and the equations of 3 asymptotes, and you're asked to explain the asymptotic behavior of the graph at a calculus level. Okay, this is the way we want to address this problem. We don't want to just say something like, well, the graph gets closer to the asymptote. We want to be a little more sophisticated than that. So there's the graph. It's pretty small on your viewing screen, but I'm going to need a bit of room to write some things down. Let's talk about the horizontal asymptote first. The reason why there's a horizontal asymptote at y equals 4 is because as the graph extends horizontally towards the right, or as the graph extends horizontally towards the left, the value of the function gets closer and closer to 4. And the further the graph goes to the right and the further the graph goes to the left, the closer and closer the function gets to having a value of 4. And we can communicate that idea by talking about a limit as x approaches infinity of the function. As x gets infinitely large, the function will get closer and closer and closer to having a value of 4. On the other side of the graph, as x approaches negative infinity, the function will also approach 4. So the limit of the function, which is telling you what y is approaching, as x extends to infinity or negative infinity, equals 4, and that's where the horizontal asymptote is. It should make sense to you based on the graph that we're looking at that as x gets larger, y on the right gets smaller and closer to 4, and y on the left, as you approach negative infinity, gets bigger, but it's still approaching 4. Just a side note here, everybody, it is possible to have functions that have different asymptotic behaviors on the left and the right. In other words, you might have, as you approach infinity, an asymptote at 4, but as you approach negative infinity, you might have an asymptote of 5. We're not going to encounter those anytime soon. So all we need to do is worry about one of these limits, and that will be where the asymptote is. Now, what about, let's talk about the asymptote that's a vertical asymptote at x equals -2. The reason why that is a vertical asymptote is explained to you in earlier grades by saying that this line, which the graph never touches, is something that the graph will always get closer to, but never reach. And what that means is as x gets closer to -2, the function takes off to infinity or negative infinity. And it's different depending on whether you were approaching -2 from the left or from the right. So for example, if I take a look at the limit as x approaches -2 from the left of the function, well, on the left-hand side of the function, the graph is moving down. On the right-hand side, the graph is moving up. So as we approach -2 from the left, the function will approach negative infinity. And as we approach -2 from the right, the function will approach positive infinity. It's not approaching positive infinity because we're approaching from the right. It's approaching positive infinity because looking at the graph when you approach it from the right, the graph extends up. When you look at the asymptote, the vertical asymptote at x equals 3, the limit of the function as x approaches 3 from the left, well, from the left, the graph is curving down, it's going to equal negative infinity for a limit. And the limit as x approaches 3 from the right of the function, well, if we take a look to the right of 3, here's x equals 3. To the right of it is over in this area. The graph is extending to positive infinity. So that's what the warm-up is getting you to think about. Have these limits expressed in terms of infinity. It is, I think, worthy of note that for a horizontal asymptote, as x approaches infinity, y approaches a number, but for a vertical asymptote, as x approaches a number, y approaches an infinity. And that should make sense because a vertical and a horizontal are opposite properties in terms of x and y. All right, now let's get to the examples. For each function, we want to determine the equations of all asymptotes and use limits to describe the function on both sides of the vertical asymptotes. I want to make a note here that's going to make our jobs a little bit easier. When you're finding vertical asymptotes, you want to factor completely. You want to take that function and make sure everything is factored. When you're finding a horizontal asymptote, you don't factor. Well, let's find our vertical asymptotes first. We want to express the function in factored form, which would be x cubed over, now I can factor an x out of the denominator and have x cubed minus 1. And what we see is there's a factor of x in the denominator, and there is also a factor of x in the numerator, which means I can cancel an x out of the numerator and denominator and be left with f of x equals x squared over x cubed minus 1. Now, just because I canceled that x doesn't mean I'm allowed to use x equals 0. This x had a non-permissible value associated with it of 0. We've canceled that x, the non-permissible value is still there, but we don't care about it today because that non-permissible value of 0 is where there's a hole. All we care about is the factors that do not cancel. So we look in the denominator of this and we can see that we will have a vertical asymptote at x equals 1. 1 is the only number that makes x cubed minus 1 equal to 0. And before we go on, what we need to do is look at the behavior of the graph to the left and to the right of 1. So I need to determine the limit as x approaches 1 from the left of x squared over x cubed minus 1. And I need to determine the limit as x approaches 1 from the right of x squared over x cubed minus 1. Now, how do we do this? Well, we do it by essentially putting in a number that x is approaching. Now, you don't have to actually calculate it on your calculator. Let's deal with the one where x is approaching 1 from the left. So as an example here, if x is approaching 1 from the left, then x might be approaching a number like 0.999. It's approaching 1, but 1 from the left means a little bit less than 1. And now what I want to do is ask myself, what happens if I put that number up top for x? By the way, since these are vertical asymptotes we're talking about, these two limits must be equal to either infinity or negative infinity. We know that because it's a vertical asymptote. So all we have to do is ask ourselves, if you put 0.999 in for x up here, will you get a positive or a negative? Well, when I put 0.999 for x in the numerator and I square it, I get a positive. When I put 0.999 in for x in the denominator, x cubed will be a number a little bit less than 1. And when I subtract 1 from it, I will get a negative denominator. And that means that this is going to be negative infinity because we get a positive over a negative. Now you can feel free to use your calculator and put this number in for x, and you will discover that you will get a very large negative number for y. And you will discover that if you continue to put in a number closer and closer and closer to 1, the result on the left will be a number that gets really large and is negative. When I do the same thing here, and I'm only going to explain this in detail, in the detail I'm doing now for this one, and as we move on, the explanations will become thinner and thinner. I'm looking here at a number like x being really close to 1 from the right, so 0.0001 more than 1. And if I put that number, the numerator will become positive because it's a positive number squared. The denominator will be positive because when I cube 1.0001, I will get something a little bit bigger than 1, which when I subtract 1 from it will leave me with a positive. That tells me that this is approaching positive infinity. So we've taken care of the vertical asymptote. Now what we want to do is find the horizontal asymptote. And this is new to you. So I'm going to rewrite down the question, which was the function is, I believe it was x cubed over x to the 4 minus x. And don't forget, for a horizontal asymptote, that we have to look at a limit as x approaches infinity of the function. And this is the only reason why I did the warm-up with you, was so that you understood that we need to find the limit of this function as x approaches infinity. And there is a little trick that we use. You identify the highest degree term. And the highest degree term in this polynomial is x to the 4. And then what you do is you divide every term by x to the 4. So we're going to have x cubed over x to the 4 over x to the 4 over x to the 4 minus x over x to the 4. Now what does this give us? It gives us the limit as x approaches infinity of, in the numerator I have 1 over x when I simplify that. In the denominator I have 1 minus 1 over x cubed. And this fraction and this fraction, as x approaches infinity, they will approach 0. The reason they will approach 0 is you're going to be taking a number dividing by an infinitely large number. 1 divided by an infinitely large number will be 0. And that means that this limit can be evaluated essentially by putting infinity in right now. If we had 1 over infinity on the top, you get 0, and on the bottom we get 1 minus 0. Well, that's 0 over 1, which means that we have a horizontal asymptote at y equals 0, because 0 over 1 is 0. Now let's just put this together. All this tells us for this function in 1a is that at x equals 1, we have a vertical asymptote. At y equals 0, we have a horizontal asymptote. We've decided that as x approaches 1 from the left, and I need to actually go back and look at it, as x approaches 1 from the left, the function approaches negative infinity, which means all we know is the graph goes down here and up there, and it must be asymptotic here and here. We can't really be sure what it's doing in between. We would have to look at more information like x-intercepts and if there are max-mins and all that stuff. Let's take a look now at the next question. B. There's nothing to factor here. So when we take a look at our vertical asymptotes are always arrived at by looking at the denominator. X is going to be equal to plus or minus root 7. These will be our vertical asymptotes. which means that we need to determine the limit as x approaches root 7 from the left of the function. And we need to determine the limit as x approaches root 7 from the right of the function. And we need to determine the limit as x approaches root 7, my mistake, as x approaches negative root 7 from the left of the function. And we need to determine the limit as x approaches negative root 7 from the right of the function. And what this is going to involve is taking a number very close to the square root of 7 for this limit, taking a number very, very close to the square root of 7, but a little bit less than it because it's to the left of root 7, and putting that number in to the function for x. If you get a negative result, then that limit I've highlighted would be negative infinity. If you get a positive result, then that limit would be positive infinity. And you would have to do that with all 4 of these limits. I'm not going to do that with you. If you want to do that on your own, you certainly can. All you would be finding here is whether the graph goes up on the left side of the asymptote or down on the left side of the asymptote. And you would repeat that for the left and the right of the other asymptote as well. I'm not worried about spending video time doing that with you. The other thing we need to look at, and it's really the new thing today, is the horizontal asymptote, which means that we need to, for the horizontal asymptote, find the limit as x approaches infinity of the function. Remember, for your vertical asymptotes, you're looking at the denominator. For the horizontal, you're looking at the limit as x approaches infinity. What's the rule here? You rewrite the limit, and you divide every term by the highest degree term in the entire expression. And the highest degree term is x squared. That allows us to get to the following point. The limit as x approaches infinity of, well, 3x squared over x squared is 3, minus 1 over x squared you can't simplify, over 1 minus 7 over x squared. And again, just like the previous question, this fraction and this fraction both become 0 at infinity. So what you're going to be left with is 3 over 1, which is 3. So you're going to have a horizontal asymptote at y equals 3. What this graph will look like based on what we have just calculated and done in this problem is at the negative of the square root of 7, you're going to have a vertical asymptote. At the positive of the square root of 7, you're going to have a vertical asymptote. At y equals 3, you're going to have a horizontal asymptote. Whether the graph with the vertical asymptotes goes down here or up here is determined by looking at the left and right-handed limits. It can't go up and down, it's going to be one or the other. But essentially, that is what we know about the graph. It has those asymptotes. Look at one more. Looking at the denominator tells us about vertical asymptotes. So we will have a vertical asymptote at x equals 0. For a horizontal asymptote, you're going to have to take the limit as x approaches infinity of that expression, which means you're going to divide every term on the top and the bottom by x cubed. Which gives us the limit as x approaches infinity of 1 minus 1 over x cubed over 1 over x this fraction and this fraction both become 0 at infinity, which means that this is equal to 1 minus 0 over 0, which is equal to 1 over 0, which doesn't exist. Well, I mean, what happens here is when you divide by 0, you get infinity. But in terms of a horizontal asymptote, if the graph is taking off to infinity vertically, then there's no asymptote. So there isn't a horizontal asymptote. If you wanted to know the behavior of the graph on either side of the vertical asymptote, then you would have to find the following limits. You would have to find the limit as x approaches 0 from the left of the function and the limit as x approaches 0 from the right of the function. And again, I'm just deciding that I don't want to do that on the video. All you have to do to find the first limit as x approaches 0 from the left is put in a number like negative 0.0001 in for x and see what you get. Remember, your left and right-handed limits for the vertical asymptotes will always be either negative infinity or positive infinity. All right, we have one more thing we want to look at today, and this is going to seem kind of weird. We're evaluating a limit of a polynomial function as x approaches infinity. Well, polynomial functions don't have asymptotes. They just continue up and down forever. But we still need to know how to do this. So here's how it's going to work. We're going to rewrite this as the limit as x approaches infinity, and we're going to factor this expression. I can factor an x squared out and be left with 1 minus x. And now what we're going to do is say that as x approaches infinity, this will approach a very big number. And the word that I've written, big, doesn't begin to do justice to how big it is. When you square infinity, you get infinity. This 1 minus x, 1 minus an infinitely large number, will be a negative number that's infinitely large. So this term, or factor rather, will be a negative big number. And don't go to university and start writing positive big and negative big in your work. You would put positive infinity and negative infinity. The bottom line is when I multiply a positive and a negative, I get a negative, and it's going to be infinitely large. All this means is that graphically, for this function, f of x, as x approaches infinity, y approaches negative infinity, all that means is the graph goes down into quadrant 4, which you certainly could have figured out by looking at the fact that the leading coefficient of this polynomial is negative. If we were to take a look at the next one, which is actually just a little bit easier because it's already factored, I believe, I want to rewrite it so I have room to add a few notes here. We've got 2x we have 1 minus 2x, we have 2 minus x quantity squared, and x minus 1. At an infinitely large value of x, 2 times that number would be infinity. At an infinitely large value for x, if I double infinity, I get infinity. And if I take infinity away from 1, I get negative, but it's still infinity. This term will be infinity. And the reason why it's positive infinity is because of that squared. It doesn't matter what 2 minus x is. When you square it, it will be positive. And if you take infinity and subtract 1 and think that you have something smaller than infinity, then you don't really have a grasp of what infinity means. You take 1 away from infinity, you still have infinity. If we multiply these numbers together, I use the word numbers lightly, I will get a negative result, which means that this is equal to negative infinity. I hope that's fine. I didn't mean to rush things by saying let's not find the left and right-handed limits. I just think that you can do that on your own and you don't need me to do it with you. Tomorrow is a Google Hangout. Same thing I'm telling all of my students. I don't see a lot of you in the Hangouts, and that's okay. If you don't have any questions, that's fine. But I hope you understand that I am more than willing to do everything I can to help you out. So if you have questions, sign in to the Google Hangout, send me an email, ask me. If you're having any difficulty, don't wait until it's too late. A reminder that your assignment is due by 3:15 today. There's your assignment for your daily work today on page 223, 3, 4, 5, and 6. You know, do every second letter. You know the drill here. And you certainly don't need to sketch any graphs or determine any intercepts. I hope that lesson made sense to you and you were able to follow it. Have a great rest of the day, and we'll talk to you soon.